Chapter 1.4, Continuity and One-Sided Limits, Day 4, the Intermediate Value Theorem. In order to use the intermediate value theorem, two conditions must be met. Number one, the function must be continuous on the closed interval from a to b. So you have a function from two numbers, it must be continuous all the way between those two numbers. What happens outside those numbers is of no relevance. And number two, there is a k between f of a and f of b. If those two things are true, then there is a c between a and b. So, for example, we have a function. Let's look at it graphically. We have a and b. The function is continuous from these 2 points. We'll say a is right here, b is right here. And it's a closed interval. And the function is continuous, means I can draw it without picking up my pen. In that interval, there is a k. We'll say in this case, k is 1. Somewhere, that graph crosses the number 1. If that's true, then there is a c. So somewhere between a and b is a value where that 1 occurs. There's an x value where that 1 occurs. This is an existence theorem. It doesn't actually find any values. It just lets us know that somewhere it happens. The consequences is this helps us know that there's roots of a function, in other words, where the function equals 0, and thus provides a method for finding these functions. This is actually what your graphing calculator does when you're asking it to find intersections. It will take your graph on that window you choose and say, okay, somewhere in here it crosses. It'll cut it in half and say, does it cross here? No. Then I use these. It'll cut it in half. Does it cross here? No. It'll keep cutting down until it gets to the intersection you're looking for. Let's use it, and you'll see more what we mean. Example, show that f of x equals x cubed plus 2x minus 1 has a 0 on the closed interval from 0 to 1. So, we're saying it crosses the x-axis. All right? So first off, we need to say that first the function is continuous, and because it's a polynomial, the function is continuous. So 1, we can say the first condition of the intermediate value theorem, f of x is continuous. And feel free to abbreviate on the interval 0 to 1. Second, we need to show that we surround the number we're looking for. If we can show that f of x is below and above, we'll see that there's a 0 between there. So first off, we'll try the left endpoint. F of 0 equals, this is simple, plug in, the x's fall off, you got negative 1. Plug in 2, or 1. F of 1. F of 1 equals 1 cubed is 1. 2 times 1 is 2. 1 plus 2 is 3. Minus 1 is 2. So what we got here is f of 0 equals negative 1. F of 1 equals 2. So we've shown it has a 0 because at one end of the interval it was below 0, and at the other end it was above 0. Graphically, it kind of looks like this. At 0, we're at negative 1. At 1, we're at 2. Somewhere in between, because it's continuous, we can't get from point A to point B without crossing the line 0. If it's a function, it's not possible. So by showing we surround the two endpoints, we show that we have found the fact that a 0 exists. And if you want to get more accurate and find out where it exists, you can cut it down and say, go, instead of from 0 to 1, go from 0 and a half and see if it's in that interval. If it's not in that interval, you check the other one, 1/2 to 1. It has to be in one of them because we know that there's 1 there. All right, this is from your book. In exercise 78, use the intermediate value theorem and a graphing utility to approximate the 0 of the function in your interval 0 to 1. Repeatedly zoom in on the graph of the function to approximate the 0 accurate to 2 decimal places. Use the root finding capabilities of the graphing utility to approximate the 0 accurate to 4 decimal places. All right, so first off, let's get out our graphing calculator. Make sure we are in radians because this is a trig problem. Hit the mode button. A screen similar to this should come up. And make sure the one that's radians is in dark. If it's not, arrow down to radians, hit enter, and it'll be in radians. You get to a clear screen then by doing second quit. All right? So we want to first show that it's continuous on the interval 0 to 1. All right? So we'll do y equals, clear out anything that might be in there. And we'll enter 1 plus x minus 3 tangent x. All right, since we're only concerned with the interval 0 to 1, go into our window right here and change the x values to go from 0 to 1. And we should see it's continuous, meaning we should see a value at the left, a value at the right, and no gaps in between. Okay, and we can see a value at the left, a value at the right, and I can go all the way in between without picking up my pencil. It is continuous. All right, so we can see that the left side is above 0, the right side is below 0. So we've surrounded 0, so 0 has to occur somewhere in there because it's continuous. There's no way we can get from above to below without crossing 0. Right? And so we're going to zoom in on the graph of the function to approximate the 0 to 2 decimal places. All right, so let's bring that calculator back. All right, now we can see that the window goes from 0 to 1. Looking at it, it appears that halfway through, about there, it's a little bit below 0. So what I want to do then is close the ink. And what I want to do then is change my window to go from 0 to 1/2. Close the window to go from 0 to 1/2 instead, and then that'll shrink the window down. If I see that it's in that interval, I'll know that instead of having a 1 gap window where the x-intercept may be, I can narrow it down to a gap of 0.5. And we can see we're above on the left, below on the right, so I can zoom in a little bit further. All right, taking a look, I can cut it in half. I can even cut it in quarters. So I'm guessing that my intercept is between 0.4 and 0.5. So I'm going to change my window to go from 0.4 to 0.5. I'm going to change my y value so I don't have to look quite so much on that. Change the y value from negative 0.31 to negative 0.5 to 0.5. Kind of just zoom in on the y-axis more. Now we'll graph it and take a look. And we can see that intercept is for sure between 0.4 and 0.5. All right, so let's zoom in a little further. Again, taking a look, it looks like probably between 0.44 and 0.47, so we're going to try it. All right, we'll change our window from 0.4 to 0.45. I better go 0.44. And this to be about 0.47. Okay, we'll graph that. Okay, so we for sure know that the first number is 0.4. The second number between 0.4 or 0.47. Let's try and get it closer. Let's change the window a little bit. I'll go down to negative 0.1 and 0.1. And let's cut this. It looked like it was closer to the right side. So let's cut this to 0.44 and 0.45 and see what that brings us. And see if we're in the window here. Ooh, looks close. All right, let's shift it a little bit. We know it's closer to 0.45 than 44. So let's make this 0.445. Make this 0.455 and see what happens here when I graph it. All right, looks like we're getting pretty close to 0.45. I'm going to call it 0.45 because all those numbers I typed in, that range is 0.45. So my intercept, my 0, is theta equals 0.45. Now, to use the 0 capability on our graphing utility, it's a little bit simpler. Let's change our window back to 0 to 1, and we'll change our y values back from to negative 1 to 1, so we can get a better look at the original graph. All right, so let's take a look. Our 0 or our root functions are in the calculus menu, which is above the trace button, and we're looking for the 0. That's number 2. So we'll select number 2, and what we're going to do is we're going to have to use the intermediate value theorem. We want to go left of the root and right of the root. So we'll arrow left here, select, we'll arrow right, select, and when we guess, we can see we got 0.45. So the repeated zooming process, that's the gist of the intermediate value theorem that our calculator uses to find zeros of a function. All right. And finally, verify that there is a value C6 of this theorem. So first off, is it continuous from 5/2 to 4? Well, we can see it's discontinuous at x equals 1. Well, 1's not between 5/2 and 4. So we're okay. We can apply it because it is continuous from 5/2 to 4. What we need to do is first find f of 5/2. Then find f of 4. So as we look at this, let's do 5/2. So if we take 5/2, store it into x, we can do x squared plus x over x minus 1. 5.833. Let's do the same thing. We'll store 4 into x. I'm going to go back up and grab my original function. You guys can do this on your calculators. I will show you how if you ask. And then just re-enter. And we got 6.67. So we can see, because we surrounded 6, that there is somewhere between 5/2 and 4, 6 occurs.